how do we define the real numbers in mathematics? Like, what is the actual formal definition of the real numbers? The informal definition of the real numbers that we often work with is that the real numbers is the set of all infinite decimal expansions, so numbers of the form an integer, dot, and then a first digit, second digit, third digit, in infinitely many digits, where the digits are between 0 and 9. But of course, one has to be careful because some expansions are equal to others. We know that the expansion 0 point followed by all nines should be equal to the expansion 1 point followed by all zeros. So in this set of all decimal expansions, you have to make an identification that expansions that end up in all nines are identified with expansions that end in all zeros and then carry a 1. So this digit, which was not a 9, increases by 1. How are we going to construct the real numbers formally in mathematics? We begin from things that we can construct from axioms, such as the integers, and from the integers we can construct the rational numbers, quotients of integers with non-zero denominator. Now, the real numbers are going to be what happens when we complete all sort of like the holes that are left between rational numbers. What do I mean? I mean that if I look at the sequence 3, 3.1, 3.14, 3.141, etc., that sequence defined appropriately will converge to pi. It's getting closer and closer to pi, but pi is a number that is not in the rational numbers. So technically, we would like the real numbers to be all the possible limits of convergent sequences of rational numbers, except that that limit is not in the rational numbers. So how can I capture things like pi that are not in the rational numbers? How can I define them just using rational numbers? What I need is to replace the notion of convergent sequences of rational numbers to some notion that says the sequence is convergent without actually mentioning what the limit is. And here's how we do it. Suppose I have a convergent sequence, so A1, A2, A3, and so on, that converges to a limit L. Then at some point, the elements of the sequence, AN, AM, they will all be close enough to the limit L. But instead of referring to the limit L, what I can say is that all the elements of the sequence are close to each other. They have to be if the sequence converges. And that is exactly what Cauchy sequences do for you. A Cauchy sequence is a sequence, AK, such that I can make the elements of the sequence at some point be all of them as close together as I want them to be. So more precisely, for every epsilon, there is an n, such that if k and j are bigger or equal to n, the elements of the sequence that are above the nth n element, they are all as close as I want them to be. The difference between the two of them is less than epsilon. And finally, we can define the real numbers as the set of all Cauchy sequences in Q. So these are sequences that are morally converging to perhaps something that is not in Q. And every one of those sequences will have a limit, and that limit represents an element of the real numbers. And except that we have to make an identification of two sequences having the same limit as being exactly the same sequence, and that is done by identifying Cauchy sequences to be the same if the limit of the difference of the elements is 0. So if they have the same limit, then they identify as the same element in the real numbers.